Hello, everyone. We would first like to thank you for being here today. We are Team Blind Solutions, and our project is Plant Nursery Management by UAV via Supplemental Guidance. My name is Chris Brown. I am acting team lead, and I'm getting my degree in Optical Sciences and Engineering.
Hi, I am Ali. I'm studying Systems Engineering.
Hi, I'm Sophia and I'm studying Electrical and Computer Engineering.
Hello, my name is Deanna Shear and I am studying Systems Engineering. Our sponsor is Bayer Crop Science and our mentor is Robert Messenger.
Agriculture has become a quick adopter of UAV technology. In production and research, crop field UAVs are guided by GPS navigation. When it comes to crop management within a greenhouse facility, GPS signaling and communication is not easily achieved. The ability to have a UAV successfully traverse an indoor facility using non-GPS communication is highly sought out for. Our mission for this project was to create an autonomous UAV that can precisely navigate a greenhouse. The drone shall be able to avoid all objects in its flight path and capture images of the crops being grown within the facility. Throughout the duration of this project, we came up on many obstacles that resulted in design changes. By the start of the second semester, we had to change the scope of our project, which caused us to start back from square one. This presentation video will focus on the work done after that point, and we will conclude on the specifics on why we were unable to utilize the supplied drone given to us by Bayer Crop Science.
The key system requirements are performance requirements, which focuses on autonomous operating without the need of GPS, environmental requirements, which focuses on the temperature, humidity level, and the water resistance, interfacing requirements, which focuses on the drone and how it will interact with Bayer inner system, the design feature requirements, which focuses on the weight and the size of the devices that will be attached to the drone, safety requirements, which will focus on the functionality of avoiding collisions and accidents, power requirements, which focuses on the power supply and the process of charging the drone and the anchors. The key design and software details are the navigation system, which the focus was on using and integrating the indoor positioning system, which are Marvelmide and POSIX, the implementation of the waypoint mission, which is a functionality built through the DJI kit, where the drone will fly to a predefined locations, the drone, which focuses on the SDK kit, the code that integrates the sensor and IPS data using the Arduino kit.
To pigeon-tail off of Ali, the indoor positioning system is the core of our project, as it pertains to the functionality of tracking the drone throughout its flight without using GPS. We executed this idea throughout a series of anchors and tags that were strategically placed around the desired area of flight. The anchors are used to determine the location of a tag and are installed at stationary positions inside a building. A tag is mobile and attached to the object to be located. Both tag and anchor are in communication with each other utilizing IMU emission signals. The timing between each signal received determines the distance between tag and anchor and enables an exact indoor positioning measurement. A series of measured frequencies allow us to determine the precise location of the drone without using GPS. The determined position is then communicated with the drone's flight controller, which adjusts the drone along its predetermined flight path.
Given the approval to change the scope where the team can now construct an open source drone, either IPS technologies can be integrated with a non-proprietary UAV much easier. This modification to the project led us to other changes that were later included in the engineering change request form. We knew that getting all the necessary parts for the open source drone would take up a lot of time to purchase and be delivered. A U of A Biosystems Engineering Associate Professor was willing to loan all necessary drone parts as well as access to the VIP lab located at the U of A's Forbes building. With this advantage, the team got to work right away. We started with constructing the drone frame similar to the DJI drone. We then soldered electronic speed controllers to the power distribution board, which is meant to work with and only with the Pixhawk 4 flight controller and GPS. Pixhawk flight controllers are highly customizable and flexible when it comes to hardware and software implementation. After mounting the radio, telemetry, power distribution board, flight controller, and GPS to the drone, and remapping and making all the right wire connections between the electronic devices, we then calibrated the flight controller and tested the motors. However, the motors would not respond during calibration. We soon discovered that the power distribution board overheated and fried. We decided to borrow and use a less complex Pixhawk flight controller, as well as using a simpler power distribution board and attaching a power management module. After calibrating this new flight controller, the motors responded and spun. From online sources, we are following a Pixhawk and MarvelMind integration manual where we are integrating and performing a simple indoor autonomous flight mission.
From the start to the end of this project, our group faced many challenges, from an initial delay in defining the project scope with our sponsors to losing a team member in the middle of our project. Our biggest obstacle resulted in a complete design change well past our halfway point. Our sponsors at Bayer Crop Science did not want this project to be a drone building one. To save us time and effort, they supplied a DJI M100, a guidance kit, and a Z30 camera, all of which had their own SDKs. Our plan was to utilize the various DJI flight path command options and to manipulate that code to allow the IPS data to be inputted instead of the GPS signaling. We determined how the beacons operate, the type of signaling and data format they send out, and how we would attach them to the drone. In the end, we discovered that the M100 was not able to directly receive non-native DJI signaling into its flight controller. What needed to be done is to bypass all DJI flight options and create a custom waypoint mission from scratch. This would be done by using rudimentary flight controls that use the signaling to be sent out by the IPS beacons. In the end, we were not able to meet all of our design requirements. From the start of the second term, we ditched DJI and continued with the open source drone. Losing the DJI, we also lost the ability for object detection and avoidance and the camera itself. The project was then split into two parts. One, to build the drone and test both IPS technologies, and two, to write up a technical report on our findings and troubles with the DJI drones in indoor autonomous flight. As Bayer Crop Science uses DJI for all UAV needs for their outdoor fields around the globe, such a report would be highly valuable.
We learned a lot along the way, boiling the lessons down to 4. The first being early scope definition and the importance of being familiar with your requirements. We learned how crucial it is to identify the risk and scope of a project before approaching the solution. With communication, we learned the difference in over-communication compared to better communication and how stakeholders need to be well informed of the situation, not just simply updated. With timing, overall, we learned that a project of this magnitude needs sufficient time to complete and more time allotment for design. With our coding knowledge, looking back, it would have been more advantageous to have more computer science practitioners on the team, as well as time for software development efforts. Leveraging a production drone product and reconfiguring the software component presented the most challenges. However, in the end, we learned that computer software is an important part of engineering and requires some level of understanding regardless of your background.
We would like to give special thanks to our sponsor, Danny Williams, as well as the additional members from the Bayer Crop Science team, Jason Licamelli and Miranda Todd, as well as our mentor, Robert Messenger, the U of A's Biosystems Engineering faculty, Dr. Kamel Diden and Dr. Armando Barreto, and finally, the Design Day instructors and coordinators.